Fourier said that any periodic function can be expressed in terms of combinations of different complex exponentials. He basically said that a function can be expressed, if this is periodic, as summations of complex exponentials with different n's and different amplitudes. Let's make this amplitude Cn, and the variable for this summation is n. Now for now, let's don't question that assumption and take it for granted, and let's try to find those n's and cn's for any function. We will now find a way to calculate those numbers for any function. Okay, let me write down a function here. Let's call it f1t is equal to 5.2 e to j 2 pi over capital T times 3t plus 7.1 e to j 2 pi over capital T times 5t. Now, if I ask you what are our cn's and n's, that's easy to find for that function. Easily we can see that here our n is 3, here our n is 5, therefore that is C3 and this is C5. Fourier series for that function is C3 is equal to 5.2, C5 is equal to 7.1. We can actually show Cn's in a discrete graph. The x-axis is n and y-axis is the amplitude Cn. C3 will have a value of 5.2, we have 7.1, which corresponds to Cn. Now look at what we did here. We have transformed a function from time domain to Fourier domain. So that is Fourier transformed version of f1 of t. Let's see another function. Let's see f2 of t is cosine 2 pi over capital T times 3t. What's the Fourier transformation for that? We know that this function is also equal to e to j 2 pi over capital T times 3t plus e to minus j 2 pi over capital T times 3t over 2. Here we can easily see that our n is 3. In this case, our n is minus 3. The graph, so the Fourier representation of this function will have two components, one in at 3, one is at minus 3, and their amplitude would be same and 1 over 2. Now we have transformed that function into Fourier domain. But now you might ask this question, sinusoidals are soft functions. What I mean is they don't have sharp edges, like they are very soft. Even if we can increase the frequency, they get a bit sharper, but still they are soft. So how can we explain a function, let's say f3 of t, such as a square wave function? How can we express this sharp function using combinations of different sinusoidals? So at this point, let me show you a demo. Okay, there's a website called www.folstat.com/Fourier where you can play around with cosine and sinus component coefficients and see the resulted summation of those components. Let me show you an example. Here at the bottom side we have coefficients for sinuses, and at the top that's the result of summation of those sinuses. Let's first add a sinus here. As you can see, as I increase the coefficient, amplitude of peak-to-peak value of this sinusoid increases. And the next sinusoid, let me take it back, and the next sinusoids has higher frequencies. Let's say if I increase this one, you will see another sinusoid with a higher frequency. Now I will try to obtain a square wave function using sinusoidals. Now let's first add large sinusoid. This has the lowest frequency and it will have the highest amplitude. It doesn't look like a square wave, but let's add the third sinusoid. As you can see, it looks a bit more like a square wave, but still it's far from being a square wave. Okay, let's add the third sinusoid, which will have amplitude 0 point around 2, and it looks a bit more like square wave now. Let's add the n7th sinusoid and make it 0.14. Okay, as you can see, as I add more and more sinusoids, it more looks like a square wave function. Now I will click this square preset and we will see a finer square wave function. Yes, this is what we will see if we add that much sinusoidals altogether. Now we have seen some examples of periodic functions and we saw how to find their Cn and n components. But actually this wasn't a mathematical way of finding those components. Rather we used intuition to finding those components. But now I will show you how to find Cn's using a mathematical formula. Now we will derive that formula actually. Okay, our assumption was a periodic function ft can be expressed as summations of various complex exponentials. And also previously we have seen that integration of e to j 2 pi over capital T n t times e to minus j 2 pi over capital T times mt dt is equal to 0 where n is not equal to m. Therefore, if we multiply that ft with e to minus j 2 pi over capital T mt, we should also multiply the left hand side mt, and if we take the integration of both sides, and this integration will be 0 where m is not equal to n. But when n equal to m, that integration will be non-zero. Therefore, using this fact, we can extract any Cn we want. Let's say if we want to extract C5, f of t is equal to summation of Cn times e to j 2 pi over capital T n t, and we multiply both sides with e to minus j 2 pi over capital T 5t dt, e to minus j, and we have an integration. We know that in this summation all Cn's will be gone. We will be only left with integration over period t Cn, in this case C5, e to 0, which will be 1 times dt. As I told you before, to make those orthogonal set of functions orthonormal, we have added a 1 over t here. So let's add 1 over t, C5. So the formula would be Cn is equal to integration over period t. Of course, we need to multiply it by 1 over t, f of t e to minus j 2 pi n. Look at, we have n here, so we need to put n here, over capital T times t dt. This is how we obtain Fourier series. That's actually the Fourier transformation of a periodic function. But the good thing about Fourier transformation is we can go back to the original function whenever we want, using the fact that f of t is equal to summations over n Cn times e to j, this time plus j 2 pi over capital T n t. Those two equations are Fourier transformation pairs for continuous periodic signals.